5,000 light-years from Earth. Nestled within the Boomerang Nebula, the temperature sits at a chilling 1 degree Kelvin above absolute zero. This is the coldest naturally occurring place in the universe. A cosmic refrigerator that makes the deep vacuum of interstellar space look like a sauna. But the strangeness of this location isn't just about the frostbite. It is about how time itself behaves when the thermal vibration of atoms effectively stops. In classical physics, we treat time as a constant background tick, a universal metronome that doesn't care if you are in a furnace or a freezer. At the intersection of general relativity and quantum thermodynamics, the story changes fundamentally. Coldness is not just a lack of heat, it is a lack of motion. And when motion ceases, the physical processes we use to define the passage of time begin to stutter and stretch. This phenomenon isn't just a theoretical curiosity found in distant nebulae. It is something we are actively recreating in laboratories on Earth, where physicists are uncovering that our perception of time is inextricably linked to the flow of entropy. To understand why time drags its feet in the cold, we have to look at what we actually mean when we measure a second. Time is not a substance you can pour into a jar. It is a measure of change. In the modern world, the gold standard for this measurement is the atomic clock, specifically those using cesium-133 atoms. These clocks work by measuring the transition between two energy levels of an atom when you cool these atoms down to a fraction of a degree above absolute zero. Their internal oscillations become incredibly stable. There is a hidden cost to this precision. According to the laws of thermodynamics, the more accurately you want to measure time, the more entropy you must create. In an environment of extreme cold, where entropy production is minimized, the very mechanism of timekeeping changes its character. If you were to place a clock in the heart of the Boomerang Nebula, the local environment would have so little thermal energy that the physical transitions defining a second would occur with a different statistical profile than they do on a warm, chaotic Earth. This leads us to the concept of time dilation caused by temperature, a field that bridges the gap between Einstein's relativity and the quantum world. We know from Einstein that gravity and velocity can warp time. But recent research into quantum thermodynamics suggests that thermal energy plays a similar role in the local flow of events. In a hot system, particles are colliding, vibrating, and exchanging information at a blistering pace. Every collision is an event, a tick of a microscopic clock. In the coldest places in the universe, these ticks happen less frequently. From a computational perspective, the universe is calculating its own evolution at a slower rate in these frigid zones. If you consider the universe as a giant computer, the processor speed in a cold nebula is effectively throttled. The density of events per cubic centimeter drops so low that the temporal resolution of reality itself begins to thin out. This isn't just a metaphorical slowing of time. It is a physical reduction in the number of state changes that can occur within a given window. Consider the behavior of a Bose-Einstein condensate, a state of matter achieved only at temperatures approaching absolute zero. In this state, a group of atoms loses their individual identities and begins to act as a single superatom. At these temperatures, the wave-like nature of matter takes over. Because the atoms are nearly motionless, their position becomes highly smeared out according to the Heisenberg uncertainty principle. When matter enters this state, the standard arrows of time that we rely on in the macroscopic world, like the mixing of gases or the spreading of heat, simply vanish. In a Bose-Einstein condensate, time appears to enter a state of suspension because the system is in its lowest possible energy state. Without the ability to move to a different state, the system cannot experience the before and after that characterizes the flow of time. It becomes a localized pocket of the universe where the fundamental clock has essentially been paused. The Boomerang Nebula itself provides a massive, natural laboratory for this effect. It is an outgoing cloud of gas from a dying star, expanding so rapidly that it cools itself through adiabatic expansion, much like how a spray can feels cold when you release the pressure. As the nebula pushes itself down to 1 Kelvin, it creates a bubble where the thermal noise of the universe is silenced. In this silence, the quantum fluctuations that are usually drowned out by heat become the dominant players. In this environment, the relationship between time and energy becomes transparent. The uncertainty principle states that the uncertainty in energy multiplied by the uncertainty in time must be greater than a specific constant. When the energy of a system becomes extremely low and precisely defined, as it does in the coldest spots in space, the uncertainty in time must, by mathematical necessity, increase. This means the timing of events becomes fuzzy. You cannot have a high-energy type of speaker, fast-moving system, and a high-precision, slow-moving system occupying the same temporal logic. We see the practical implications of this in the way we design quantum computers. These machines must be kept at temperatures colder than deep space to function. The reason isn't just to keep the wires from melting. It is to slow down the interaction between the system and the environment, a process called decoherence, when a quantum bit, or qubit, is kept in extreme cold. Its perception of time is altered. It stays in a state of superposition for longer because there isn't enough thermal energy in the surroundings to kick the qubit and force it to choose a state. By cooling the computer, we are stretching the amount of time the quantum state can exist before the rest of the universe catches up with it. We are creating a microenvironment where time moves differently to preserve information that would be destroyed in the heat of a room temperature room. This connection between cold and time also touches on the heat death of the universe. In the far distant future, trillions of years after the last stars have burned out, the entire universe will approach the temperature of the Boomerang Nebula and then go even lower. As the temperature drops, the rate of all physical processes will slow down. The intervals between events, the birth of a star, the collision of a black hole, will grow longer and longer. Eventually, the universe will reach a state of maximum entropy at a temperature of nearly absolute zero. At this point, time effectively ceases to have meaning. If no 2 points in the universe can exchange energy, no change can occur. Without change, there is no way to distinguish one moment from the next. The cold, in this sense, is the ultimate thief of time. It represents the transition from a dynamic, temporal existence to a static, eternal one. Scientists at the Cold Atom Lab on the International Space Station are currently pushing these boundaries, creating temperatures 10 billion times colder than the vacuum of space. By doing this in microgravity, they can observe atoms for longer periods without them falling to the bottom of the container. What they are finding is that at these extremes, the very concepts of fast and slow lose their traditional meaning. When you are looking at atoms moving at a few millimeters per second, the scales of time we are used to in our daily lives, the milliseconds and microseconds, become irrelevant. You are entering a regime where the geometry of space-time is the only thing left. There is a growing body of evidence suggesting that at these temperatures, we might be able to observe time crystals, structures that repeat not just in space, like a diamond, but in time. These crystals pulse without consuming energy, essentially breaking the time translation symmetry that governs the rest of the known world. If we look at the math of thermodynamics, specifically the Clausius inequality, we see that the change in entropy is always greater than or equal to the heat transferred divided by the temperature. When the temperature resides near zero, even a tiny change in energy creates a massive swing in entropy. This makes the local arrow of time incredibly sensitive. In the coldest place in the universe, the link between the past, present, and future and future is stretched thin. While a human observer in the Boomerang Nebula wouldn't feel like they were moving in slow motion because their own biological processes would be the clock they were using, an outside observer would see a system where the fundamental building blocks of reality are behaving with a lethargy that defies common sense. The colder a system gets, the more it detaches from the frantic pace of the rest of the cosmos. This divergence is most notable when we consider the speed of sound in ultra-cold gases. In a room-temperature gas, sound travels through the fast, chaotic bumping of molecules. In an ultra-cold Bose-Einstein condensate, sound travels as a wave through a superfluid. These waves, or phonons, move at a pace dictated by the quantum properties of the fluid rather than thermal energy. Because these systems are so quiet and cold, they can be used to simulate black holes, specifically sonic black holes, where researchers can study Hawking radiation by creating a flow of cold atoms that moves faster than the speed of sound in that medium. Scientists create an event horizon. This shows that cold temperature allows us to manipulate the flow of time and information in ways that mimic the most extreme gravitational environments in the universe. The cold is a portal to physics that is usually hidden by the noise of heat. Furthermore, the relationship between cold and time is reflected in the very long baseline interferometry we use to map the cosmos. Our sensors must be cooled to incredibly low temperatures to reduce thermal noise. When a sensor is warm, its own atoms are vibrating so much that they create a time blur in the data. By cooling the sensors, we sharpen the temporal resolution of our images. This reveals a profound paradox. To see the universe's past more clearly, we must exist in a state where time moves more slowly and steadily. The cold provides the stability required to witness the high-speed chaos of the distant energetic universe. We are using the stillness of the cold to capture the fleeting moments of the hot. The Boomerang Nebula and the labs that mimic it teach us that time is not an independent variable. It is a product of the interactions between matter and energy. When you remove the energy, as you do in the coldest place in the universe, you are essentially removing the lubricant that allows the gears of time to turn. The slowing of time in the cold is a reminder that we live in a universe of motion. We are creatures of heat, existing in a narrow band of temperatures where time moves at a pace conducive to life and complexity. If we were to stray too far into the cold, we would find a universe that is not just freezing, but one where the very sequence of events that defines our existence begins to unravel. The cold isn't just a physical state, it's a temporal boundary. Understanding this allows us to rethink the history of the early universe. Directly after the Big Bang, the universe was unimaginably hot, and time moved with a violent intensity, with trillions of crucial events occurring within a single microsecond. As the universe expanded and cooled, the pace of cosmic evolution slowed. We are currently in a temperate era, but as we look toward the coldest places in space today, we are seeing a preview of the end of time itself. The Boomerang Nebula is a localized pocket of the future, a place where the universe has already begun to go quiet. It challenges our perception of the second as a fixed unit, showing us instead that time is as flexible as the temperature of the atoms measuring it. To wrap it all up, the next time you think about the vast, empty cold of space, don't just think of it as a void. Think of it as a place where the cosmic clock is winding down. The strange physics of the Boomerang Nebula shows us that time, entropy, and temperature are a single braided thread. By exploring these frigid extremes, we are not just learning about liquid nitrogen or frozen gases. We are peering into the machinery of reality itself. We are discovering that for time to exist as we know it, the universe must be burning. In the deepest cold, the fire of time goes out. leaving behind a static landscape where the now lasts forever. Take a moment to consider how the simple thermal energy in the room around you is actually the engine driving your personal experience of the future. Subscribe for more explorations into the deep mechanics of our universe.